Bayes formula. So here at the beginning of this, I have I worked out an example for you to review and read. It's a probability of an earlier event given at a later event. So, we've been solving for what is the probability of something happening. In this section, we're going to find the probability of a later event based upon an earlier event. And if you wanted to, you can pause this and read it. This is an example. It goes together. I thought it was pretty neat. Take a picture of it. It will help you work out some of the problems or have a better understanding. So it's a long example, but it answers the question. So now let's move to this part here. Let's actually solve some. It says example 1, we're going to write the expression as an integer quotient and reduce the lowest term. So this problem is very, very important because you got to be able to do the basic math of it before you jump into the application part. So what I see here going on is I have fractions and fractions. It's complex. However, it's easier if you can just work on it in parts. So I'm going to rewrite it just for myself. I'm not saying you have to, but sometimes it's easier to see it when you rewrite it. All right, so let's get this rewrite. And remember, we got to obey the rules of order of operations. All right, so now I notice in the first two fractions, the 9's reduce. So let's reduce it. So now I get 5/2. Divides. In this other parenthesis, what do I see? The first two here reduces again by 9. So I'm going to bring it down and I have 5/2 here. Let's clean this up, write it a little neater. And it's going to be added to. Well, these last two here, there's nothing it reduces by, so I'm going to multiply straight across. So I have 1 times 1, 2 times 5. All right. Since this is still the denominator, I cannot divide. I cannot do this part yet. I got to clean up that parentheses. So let's go ahead and do another step. Now, in order to add the 5/2 plus the 1/10, we have to have a common denominator because it's a fraction. And I notice that 10 will go into 10 and so will 2. So I'm going to multiply this fraction by 5 over 5. And now I get 5 times 5. Over 2 times 5 plus this, and I'm doing an extra step, guys. You do not have to do this. I get 25 plus 1 all over 10. So that worked out great. So now let's finish up. 5/2 divides 26/10. I can go ahead and reduce this now if you wanted to, and then do the rules for division of fractions. Sometimes it's easier, so let's go ahead and do that. I noticed that 26 can be reduced by 2. 2 goes into it 13 times. 2 goes into 10 5 times. So now I have 13/5. Right? Now let's do the keep, change, flip. Keep, change from division to multiplication, and flip. Now that I've already reduced it, I can't reduce no more. We are down to the smallest form. So 5 times 5 is 25. 2 times 13 is 26. And this is my final answer. Okay. So now let's do example 2. It says find the probability for referring to this tree diagram below. And we're solving for M intersects A. So here's M and here's A, where we're taking the probability of M and probability of A if happens in the event, is in the event of the group M. All right. So now let's just solve. So what do I know? I know the probability of M, it's given to me. It's 0.1. The probability of A happening in M, well, that's given to me too. It's right here, 0.2. So now we want to multiply those two together. Isn't that what it says here? So when I multiply those two together, I get, and that is my answer. So 0.02. Let's do example 3. We're going to find the probability by referring to this tree diagram again. We're given this formula that we're going to be working with to solve it. So we are looking again at M and we're looking at A. So if we're looking to see this group that has A occurring and happening, you know, and A's been given to us. So we're going to have to do a little bit of work to solve for that. So, and this, let me see if I can get that line to go away. There we go. Now you can see what we're working with. So let's write this down. What do I have? Well, we need to come over here and write this right quick. We have the probability of MA means that I'm going to, and if this will help you, I'm going to do another step right quick. Let me just do this. The probability of M intersects A, we know it's going to be the probability of M times the probability of A in M. All right, and then they said down here, the probability of this intersection plus the probability of this intersection. Why are we worried about the N? Because A occurs in N as well. Okay, so that means that I got the probability of M times the probability of A in M, oops, plus the probability of N and the probability of A in M. There we go. All right, that looks good. So now let's just plug in what we know. Well, the probability of M is 0.8 right here times the probability that A occurs in M. It's here. Divided by, so we're going to have that same thing here. And then we're going to add it to this here, the probability of N, which is 0.2, times the probability of A occurs in N. So let's do some math. Let's multiply. We got 0.8 times 0.4. That's 0.032, 0.32. I said it backwards there. 0.32 plus, we got 0.2 times 0.6, 0.12. Now let's add the 0.32 to the 0.12. And now let's divide. 0.32 divided by 0.44. And let's round to the nearest hundreds. And that answers the question. The probability is approximately 0.73. Example 4 says that we have two groups. Okay, so we have a whole entire sample. It's called S. We get the whole thing. And then we have two groups, U1 and U2. So we're going to use the Venn diagram and we're going to use the Bayes formula. We're going to assume that simple events is S and it's equally likely. We're going to solve for where in that group 1 R occurs. Okay, so we have these formulas that we're going to use. Let me, right here, I've got it written down for you. All right, now let's solve. So when I go back up here and look, what do I see? I got the, let's just label it right quick. It might make it easier. in this group 1, I have an intersection of R. And if you'll see, it's right here. The R is in the blue. So this is 30. The total number of samples in this sample space, well, we got 10 plus 30 plus 40 plus 20. So what do we have? We have 100. So now to figure out what our probability is, let me erase this right here because that's the number of samples. Let's figure out the probability. When we figure that out, the probability of this event happening, right? We're going to have this here. So I got 30 divided by 100, which is approximately 0.30. All right, but you don't have to put the 0 on the end because it's just a trailing 0. All right, so we know that much. Now let's look at the 2. Let's look at what happens in 2 because R occurs in both places, not just 1. So if I want to find the probability of this happening in the group 2, well, it's 40 in group 2 and the total sample hasn't changed. So we got 0.4. So we're doing good. The reason we need that is because when we plug it into our formula for this here, right here, to solve, we need to know that second group, as you noticed above. We did it in our previous. So we can call ER. In this case here, we can call that R. So now I have this over this plus this. All right, so now we got our formula. Now let's break it down. The U or group 1 intersects R at 0.3. It's all divided by 0.3 plus the second group intersects R 0.4. So now I got 0.3 all over 0.7. And when we divide this out, we get approximately, let's go out to thousandths, 429, 0.429. And that is that probability. Okay, example 5 says that we have this group W, and where the C complement occurs in that group. And we have this triangle here, or not triangle, we have this tree diagram here to use and it gave us our information. And if you notice, here's the C complement, C complement, C complement, here's the W. So we got 3 groups going on here, right? And 2 outcomes in each group. So let's solve for this. So what we need to do is let's go ahead and do the product branch of, and we're going to call this here our C complement, and we'll call this here our W. All right. And when we do that, what do we have? Our C complement is 0.8 and our W is 0.7. So we're going to multiply those 2 together. Okay, so far so good. Now we need to figure out what's the denominator. So it's the sum of all of them. Well, if you notice that C complement played in a lot of places. So first things first, we need to see what we got going on here. We have C complement of the V, which is going to be 7.7 times 0.2, right? So if you want to, you can come over here and make note on that. If you want, or you can put it down here. Just make sure that your notation is, or do it like this. This may be helpful. Okay, so this one's going to be 0.2 times 0.7, which is 0.14. this one here is going to be 0.6 times 0.1. So we get 0.06. Okay, now we're good. Now what we're going to do is we're going to take the sum of them. So we're going to take that and we can write it down here underneath that denominator to help see it. So now that I took all those, I take the 0.56 plus 0.06 plus 0.14, add those up and I get 0.76. And now divide those out and I get 0. And we're going up to the nearest thousands, 737. And that's the answer for that one. Okay, now let's go to example 6. It says one of 2 urns is chosen at random. Which one is likely to be chosen as the other? Then the ball is withdrawn from the chosen urn. Urn 1 contains 1 white and 5 reds. Urn 2 contains 3 whites and 3 reds. Okay, so if a white ball is drawn, what is the probability that it came from urn 2? So we want to know the probability it came from urn 2. So it may be helpful if you wish to draw out our tree diagram. We have 2 events or 2 items, 2 groups. We have urn 1 and urn 2. Urn 1 has an option of white and red. So does urn 2. Okay, so now we need to figure out what's going on. Or we need to label this. You know, the previous one gave it to us already. So let's figure this out. So the probability, urn 1. Well, there's one group of urn 1s and there's 2 urns. So that probability is 1/2. Makes sense. Okay. Well, that's the same for the second one as well, right? Because there's only 1 urn 2. And there's only 2 in that whole entire thing going on, right? There's only 2 of them, 2 urns, right? All right, so now let's figure up our probability of the white in urn 1. Well, if you look here, we have 1 white plus 5 reds. That's a total of 6 in that urn. And there's only 1 white, so I have 1/6. Okay, so then now let's figure out what is the probability that the red occurs in that urn 1. Well, there's how many reds? There's 5 reds and there's a total of 6 in there. Oh, and we need to put these on our thing here. So we got 1/6, 5, 6. That was the whole point. Put it on there. All right. So now let's talk about the white in the second one. So there's 3 whites, 3 reds. So there's a total of 6 here again. And there's 3 whites, total of 6. Of course, you don't want to say 3/6 because it's not reduced. We always reduce the simplest form, so it's 1/2. Now we got the red in that as well, and there's 3 reds, total of 6. It reduces to 1/2. All right. Now we're gonna start cranking the numbers together and answering and solving. So we're going to multiply the branch probabilities leading that there is whites in group 2. So in group 2, what do I see? We have probability of U2 in the whites. We have 1/2 times 1/2, which gives me 1/4. And if this helps, look, there's a lot of halves here. All right. Now, that we have that, we can plug it in. And I'm not done, so give me 1 second. Let me just put a bar in because we're missing the other part of the formula, right? So now the denominator part, what do we got going on there? So we want the total to go in the denominator. What do I have? We have, remember, if we're looking at the 2, we got this 1/4 already figured out right there. We're doing the intersections here. Let me write the formulas because, you know, sometimes that just makes it a lot easier. I just kind of skipped the formula. Let's not do that. We're doing the probability of the intersection of U2 and Watts. Then that means the probability of U2 here intersects Watts plus the probability of U1 intersects W, right? We don't want to mess this up. So now I have a half times a half, all divided by half times the half, plus, what do we get? 1/6 times that half. So now I got 1/4 over 1/4 plus 1/12. I got 1/4 over, multiply this by 3 to get the common denominator. So I got 3 plus 1 over 12. Let's rewrite this. I got 4 over 12. And we can reduce that if we wanted to. Let's go, because 3 plus 1 gave me that 4. So let's go ahead and do that. So give me this. Now let's rewrite it. Keep, change, flip. And then round to the nearest hundreds. And that is my answer. Okay. Let's do example 7. It says a new simple test has been developed to detect a particular type of cancer. The test must be evaluated before it is put into use. Medical researcher selects a random sample of 3,000 adults and finds that 3% have this type of cancer. So each 3,000 adults is given the test and it found that it indicates 95% of those who have it and 2% of those who do not. Based on these results, what probability of randomly chosen person having cancer, given that test indicates cancer, of a person having cancer, given that the test does not? So we're looking for does and does not, you know, indicate they have cancer. So let's set it up. Let's do this. Let's say we're going to let C equal cancer. We're going to let the C complement no cancer. We're going to let T be the test that indicates cancer. I'm going to abbreviate, well, indicates cancer. It's going to abbreviate, but nah. Let's let T complement indicate the test, or the test indicates no cancer. Okay, and if you want to, you can come over here and start our tree. So what do we know? We have 2 groups. We have the cancer and the test that indicates with cancer, test that indicates no cancer. Then we have the patients no cancer, take the test, has the indication they have it, and take the test, the indication they don't. So now let's look at it and solve this right quick. So we're going to take the probability of C, of cancer. And if you notice, they said 3% have this type. So we can't answer it as 3%. So we're going to divide by 100% to undo the percent, or you can move the decimal 2 places to the left because there's 1, 2 zeros here. We get 0.03. So that tells me it goes here. Now we're going to find its complement. To find its complement, we know it's 1 minus that event. So I got 1 minus 0.03, which gives me 97, or excuse me, 0.97. All right, and that went there. Okay, so the next thing we need to identify the probability of the test. So I'm going to say, okay, the probability of the test, right, that indicates they have cancer to in the group of the cancer patients. So what did they say? Here it said 95%. Of course, we got to undo the percent, divide by 100, or move the decimal 2 places to the left. All right, so now I know this one. Now define the complement of it. The test complement. We know we're going to subtract that from 0.95. So I get 0.5, 0.05. All right. Now let's solve for the test on the patients that do not have cancer or complement, yeah. It's no cancer. So when we do that, we notice the 2% here says do not have it. And again, we're going to have to undo the percent. All right, so that goes right here. Now, let's find the complement of the test. We're going to take 1 minus that. Okay, we're almost done. So now let's solve for this. We're going to plug it in this formula, 0.3, look, 0.3. Second. So we plug it in there, we get 0.03 times. So we go back to the original formula that we've done. So remember, this came from the intersections of them. So we got 0.03 times 0.05 all over 0.03 times 0.05. We're going to add it to 0.97 times 0.98 and type that in the calculator. We'll get 0, 0, and we rounded, so 1575.